So now that we've talked about how to find domain, we're going to talk more specifically about what's happening if we have a restriction in our domain. So we're going to talk about points of discontinuity. A point of discontinuity is going to be a point on a graph where it's not defined or it doesn't exist. We're going to look at two different types. We're going to look at what we call removable points of discontinuity, which basically means that once we take our rational expression that we've already been dealing with and we set it up in terms of what do I do to factor the top, what do I do to the factor the bottom, any factors that are going to cancel, the values that made that factor have a denominator of 0 are going to be removable. That sounds really wordy. We're going to look at some examples and it's not going to be as bad as it sounds. But basically what happens is that we can cancel or reduce factors, then that is going to be a removable point of discontinuity. In terms of what's happening when we look at the graph, if I look at the graph where there's a removable point of discontinuity, I'm going to have a hole there. And I'm going to show you, or you can see below already, what a picture of that looks like. In terms of non-removable points of discontinuity, that's going to be if we factor and we can't make the factor that gave us a restriction in the domain, we can't make that go away, then that's a non-removable point of discontinuity. And what we're going to have there is something that we call a vertical asymptote. So notice like right below these definitions here, I have a couple pictures. So let's look at these pictures. So first of all, look at this first rational expression I have. I know it's a rational expression because it has essentially a function on top, x plus 1 times x minus 1, and a function on bottom, x minus 1. Notice that this is already in factored form for me. So when I go to reduce this, well, first of all, if I list my domain, and I always list my domain before I reduce, if I list my domain would be that x cannot equal 1. So that's what we've done so far. But what if I take it a step further and say, why can't it be 1? What's happening on the graph? Well, since the x minus 1 cancels out, that's going to be a removable point of discontinuity, and I should have a hole there. So check this graph out. So my new function after reducing is x plus 1, which is a linear function. So I start at a b value of 1, and I rise 1, run 1. But notice that when I rise 1 and run 1, when x is 1, since x cannot be 1, I have to put a tiny little circle there. Then I continue to rise 1, run 1, rise 1, run 1, and I can continue my graph on. The rest of my graph is very similar, exactly the same as the linear functions that we've looked at in the past. It's just at that one x value that I have to acknowledge that I can't actually be that x value. So again, what do I use? I use a little hole. If I look at the second one here, notice on this one, it's already, well, I guess I could say it's already in factored form. It can't really be factored. Notice that nothing will cancel out. Well, when I list my domain here, my domain is the exact same as the last one, x cannot equal 1. But this time, where on the last one I could cancel that factor that gave me the problem, this time nothing's going to cancel that x minus 1 out. So that's going to remain a problem. We call that, again, a non-removable point of discontinuity. So when we look at the graph, we get this imaginary line. This line that's drawn in purple here does not really exist. It's drawn in here for you to see it. But this on a graph, if you were to look at, say, for example, a graphing calculator, if you graphed this, you're not going to see this purple line here. But what's going to happen is this function is going to continue to go up, 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 and get closer and closer to 1, but it's never going to actually reach an x value of 1. It's going to get infinitely close to it. Same thing coming from this direction. It's going to get closer and closer and closer to an x value of 1 as it drives further and further down, but it's never going to actually reach it. That is what a vertical asymptote is. So, removable, we get a hole. Non-removable, we get an asymptote. So, let's look at two separate examples here. So, on each of these, we're going to list the domain, then we're going to tell what the points of discontinuity are, tell if they're removable or non-removable, and then state what's happening on the graph. So looking at the first one, this should be a fraction. First thing I'm going to do is I'm going to factor it and say I get y equals x plus 3, factors of -6 with a sum of 1 because it's just x squared, so I can use my factor sum table and plug my answers right back in. Well, I know that 3 times -2 gives me -6, and 3 plus -2 is 1, so I get x plus 3 and x minus 2. So my domain is that x cannot equal -3 and x cannot equal 2. In simplified form, I get y equals 1 over x minus 2. So since the factor of x plus 3, the factor that gave me a restriction of x -3 is gone, I'm going to go ahead and say that at x, well, I'm going to do this actually. No, I will do it this way, sorry. At x equals -3, a removable point of discontinuity and a hole, since holes occur at removables. And I'm going to cover up my directions here. And I'm going to say at x equals 2, a non-removable point of discontinuity and a vertical asymptote. So again, taking what we've already done, listing the domain, and now just extending it and saying, okay, so what's happening at the domain? So can we be a little bit more specific? But other than that, exact same thing that we've already been doing. Not a lot of new concepts other than understanding what's removable and what's happening at removable, a hole. What's non-removable and what's happening at non-removable, a vertical asymptote. So B would be a good one for you to try. Now that you've had a chance to pause the video and try one, let's see how you did. So first thing I'm going to do is, just like before, I'm going to factor it. I'm going to say that this is x plus 3. Since I'm in the form a squared minus b squared, that's going to be x plus 3, x minus 3. So my domain is going to be that x cannot equal -3 and x cannot equal 3. Well, notice if I were to reduce, my x plus 3's will reduce, leaving me with 1 over x minus 3. Well, the x plus 3 went away, and the x plus 3 is what caused -3 to be a problem. So I'm going to say at x equals -3, I have a removable point of discontinuity and a hole. While at x equals 3, because x equals 3 is still a problem, it would still make my denominator 0. So at x equals 3, I have a non-removable, which I'm not going to be able to fit that in there, so I'm going to say a non-remove, of discontinuity and a vertical asymptote. And that is it for this video. Just remembering that removable, hole, non-removable, vertical asymptote.